Now we want to talk about the idea of primary intermolecular force. So we have this chart that shows all the different types of intermolecular interactions, and it shows their relative strength. And we've said that these intermolecular forces affect and inform how molecules organize. Okay, so they affect how molecules would arrange spatially next to each other. We're not going to be breaking bonds, just kind of how are they going to situate next to each other? How much do they want to stay close together? How tightly are they bound together? You can see there's relative strength in the ordering. London dispersion is weaker than dipole-dipole, is weaker than hydrogen bonding. And so these things are not created equally. Some molecules will be capable of forming more than one type of interaction, but one of them will be the primary interaction, whatever's the strongest. So hydrogen bonding would always be primary. If that's not possible, dipole-dipole. If that's not possible, dispersion forces. And this primary interaction is going to determine how the strength that the molecules are held together with and how they kind of arrange. Are they arranging based off an individual covalent bond, the whole molecule, or random chance? And so, that's going to kind of inform what they look like, how they arrange, and those sorts of things. So we want to be able to parse out what's the primary intermolecular force, because that's going to be the most important. These water molecules that we're showing here, yes, these can form dispersion. They can form dipole-dipole, but the hydrogen bonding is so much stronger that the water molecules will arrange based off of that. It's not worth it to break a hydrogen bond or to disrupt that formation in order to arrange a dipole-dipole interactions. So the relative positions of molecules will be based around hydrogen bonding. All right, so we want to look at some examples here. What types of intermolecular forces are possible for each molecule? What is the primary intermolecular force for each? So whenever we're determining properties of molecules, anything like that, Lewis structure is always going to be our best place to start. We know Lewis structure is what we want to take a look at. So once we have the Lewis structure, in terms of figuring out what types of intermolecular forces are possible, there's 3. And generally the order we want to check things in is first, can the molecule form hydrogen bonds? Second, is the molecule polar? And third, can the molecule do dispersion? The reason why we go in this order is once you hit a yes, all questions below it are also yes. So a molecule that can form hydrogen bonds is also polar, and it can do dispersion. Also importantly, this is the order of strength. Hydrogen bonds are the strongest, then dipole-dipole, then dispersion. So that tells you what the primary intermolecular force is. I'm not sure if we mentioned it, but IMF is the common shorthand for intermolecular force. So we get our nice little shorthand here. We know that when we pick that primary intermolecular force, we're done, right? That'd be what we want here. So we if we go in this order, you don't have to go in this order, but going in this order makes it easier, or it kind of removes some other questions, shortens it a bit, and it get some bang for your buck. You also pick up primary. H2. So H2, hydrogen molecules. Just a hydrogen atom single bonded to another hydrogen atom, no frills, no lone pairs. Can this molecule form hydrogen bonds? I mentioned hydrogen bonding was confusing in terms of name. No, hydrogen cannot form hydrogen bonds. Remember, you have to have the covalent bond between a hydrogen atom and then oxygen, nitrogen, or fluorine. Even just at the level of the formula, just only hydrogen atoms, this thing cannot form hydrogen bonds. As confusing as it is, the covalent bond between nitrogen atoms is not a hydrogen bond. Hydrogen bonds are a type of intermolecular force that is a solid line. It is a bond, not intermolecular. Is it polar? Well, this is just 2 atoms, so it's a single bond. Is the bond polar? These are the same atoms. It's non-polar, so no, it's not polar. Can this molecule do dispersion? This answer is always yes. Every single molecule. The prerequisite for doing dispersion is having electrons. This molecule has electrons. Yes, it can do dispersion. H2 can only form dispersion interactions because it's nonpolar. Once we know it's nonpolar, they can only form dispersion. So that's the primary intermolecular force. It is the weakest of the intermolecular forces, but it's the strongest that hydrogen atoms can do. Thus, it determines how they interact. hydrogen is just like a random jumble. Hydrogen molecules just kind of jam together when they are in the solid, because there may be some patterns that start to form, but for the most part, they're just going to be kind of jammed together because they're just close together, random instantaneous and induced dipoles form. They just jam. There's not much order because they have a very weak intermolecular force in the form of dispersion. Carbon monoxide, CO. Can this form hydrogen bonds? This time it does follow what makes sense. No, because there's no hydrogen. If there's no hydrogen molecule, no hydrogen bonds. Is it polar? Different atoms in my 2-atom molecule means it's polar. So yes, carbon monoxide is a polar molecule. Can it form dispersion? Once I answer yes at the polar, every other answer is going to be yes. Dispersion is always yes, yes, yes. And so carbon monoxide can form both dipole-dipole interactions and dispersion interactions. But the primary is going to be stronger, where we got our first yes answer on polar. So dipole-dipole interactions are going to be the primary intermolecular force for carbon monoxide, because that's what holds it. That's stronger. Dispersion, who cares? You want to maximize that polarity. So since it's dipole-dipole, since that's the primary intermolecular force, now my molecules are going to be polar, and they're going to arrange in a pattern. There's going to be a lot more order when these molecules come together, because there's these dipole-dipole interactions that, make it, useful to kind of line up in a certain way, kind of form these shells where you're going to have those interactions. And when we're talking about dispersion in this context, when we say that a molecule can be both, kind of dipole-dipole and dispersion, one of the ways we can think about it is that there are kind of random fluctuations that make the dipole interactions a little more stronger, or they kind of go in other directions that aren't already in the permanent dipole. And so these kind of fluctuations, the electrons are still moving, and they kind of, like all of a sudden, this gets a little more positive, so it has a little stronger interaction with this negative. It still is attractive. It doesn't just not matter. It just doesn't inform how the molecules arrange with each other. NH3, ammonia. Can this molecule form hydrogen bonds? You bet. Nitrogen is covalently bonded to hydrogen. This molecule forms hydrogen bonds. All molecules that form hydrogen bonds are polar, so you would know that right off the jump. But you can also tell that this molecule is polar based off that lone pair on the central atom. It's not just 2 atoms like the CO and the H2. It's nitrogen, a central atom bonded to outer atoms. Lone pair on the central atom means it's a polar molecule. Can it form dispersion? 3 yeses, yes, yes, yes. Dispersion's always yes. So ammonia can form everything. It can form hydrogen bonds. It can form dipole-dipole interactions, and it can form dispersion interactions. Okay. But hydrogen bonding is primary. When these molecules interact with each other, it's all about forming these hydrogen bonds. It's all about, you're not worried about the overall kind of molecular dipole. Again, dispersion kind of fluctuates, that makes the hydrogen bonds maybe a little more strong, or you kind of get dipoles going in other directions that kind of hold things together. But overall, the pattern, it's going to be based off forming these hydrogen bonds. That's going to be the determining factor for what the overall shape of this molecule, of the arrangement of molecules in a bulk phase of ammonia. And again, those Lewis structures are, right angles. The real molecules do have a trigonal pyramidal geometry. And they do arrange, the hydrogens linking in with that oxygen, nitrogen, hydrogen, nitrogen, hydrogen, nitrogen. C6H6. And this looks like a pretty daunting Lewis structure. This condensed formula doesn't imply any of this. Okay, so we'll see that we don't even need the Lewis structure for this one. Because if we go through our questions, can this molecule form hydrogen bonds? Well, no oxygen, nitrogen, or fluorine, so no. So we know we're good on that one. Is it polar now? No, normally this is where we maybe use the Lewis structure. But this is an organic molecule that only contains carbon and hydrogen. Only carbon and hydrogen means it's nonpolar. It doesn't matter what the shape of the molecule is, what the kind of arrangements are. When you put carbons and hydrogens in the molecule, it's always going to be nonpolar. And we can think, what really happens is this like carbon hydrogen maybe pulls that way. This one pulls perfectly in the opposite direction. This molecule is so nonpolar. They are all pulling in opposite directions. The carbon-carbon bonds aren't polar, and then you're just getting all of this. This is perfectly nonpolar. It can only do dispersion. So C6H6 can only form dispersion interactions. That means that's the primary force. I'm not going to show a bunch of these molecules jammed up together, but it's only dispersion interactions. That's a relatively weak force for them. CH3OH, we've got the Lewis structure here, comes from the condensed formula. Can this molecule form hydrogen bonds? Yes. The O is bonded to hydrogen. You can definitely form hydrogen bonds on this. Is it polar? Well, it's C and H like we saw previously, but now there's that oxygen in there, so we certainly would expect that it's probably polar because of that oxygen. Also, because it can form hydrogen bonds. Once we know that, we are done. That's a polar molecule. Can it form dispersion? Yes, because all molecules can form dispersion interactions. So CH3OH can form, again, all three types of interactions, but hydrogen bonding is primary. So we actually previously looked at what it looks like when these molecules line up next to each other, and it's all based around hydrogen bonding. Hydrogen bonding is going to drive the relative arrangement of molecules because it's the primary intermolecular force. Participation 828, question 2. What is the primary intermolecular force for each compound? A is HF, B is H2O, and C is C2H6. This is the second question on participation 828, due Friday, August 28th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the primary intermolecular force for each compound? A, we've got this HF molecule, B, H2O, and C is C2H6. These might look a little familiar. We've done some analysis of them already. You don't need to reinvent it. We can reuse some of that insight. And again, second question, we already had the first question last video. Second question, there'll be a couple of questions that all might have, this one again has 3 parts. It might not have multiple parts each, but that's one question. So determining primary intermolecular force tells us how strongly molecules are attracted to each other, how those molecules will arrange in space, right? What is the kind of arrangement of those molecules? How do they want to interact with each other? And so molecules are organized to maximize those interactions, right? And so knowing what those intermolecular forces are going to inform all of the bulk properties of the substance. Because what is the liquid like? What is the solid like? It's all going to be based around, well, how are those molecules attached to each other? How are they connected in? How are they arranging in such a way as to maximize those interactions? And primary intermolecular force is going to determine and help inform all bulk properties. So why is water wet? Because it can form hydrogen bonds. That is not joking, literally what's going on here. And so those ideas are all going to be really important. So now we can take these ideas from intermolecular forces and start talking about those bulk phases that we started off describing in chapter 10. Okay, got another question for participation 828 in this video. We won't always have, there won't be one question per video. So far, we're at that pace. They'll just kind of randomly arrange. Sometimes they'll be front heavy. Sometimes they'll be evenly spread out through videos. Who knows? Keep watching videos, find more questions. See you there.